So hi everyone, my name is Florian Koras. I'm a Cisco software engineer. I'm working here generally on SDN sort of stuff. In particular, I'm looking at programmable overlays. And I generally tend to look at solutions that involve this protocol called LISP, the Locator ID Separation Protocol. And I've been contributing to open source, but nothing really compared to what the people here in the room do on a daily basis. So I've worked on Lisp Mob. By the way, a show of hands, does anybody know what Lisp is? Wow, that's pretty good. I have low expectations. I've been working on Lisp. Lisp Mob is an open source implementation of Lisp for Linux, Android, and OpenWRT, but just basically the control plane, nothing of the data plane. And after that, I started working a bit in the control plane per se, which is ODL. I've contributed there a bit in the Lisp flow mapping project. And now, well, of course, some of you may know, we're working on the Overlay Network Engine project, or for those intimate with it, we call it the One Lisp. And yeah, let's get into it. Instead of giving you trying to run through the code and give you lots of details, I'll first try to give you a bit of a high-level view of what we expect to do with this project, where we are at. Then we'll do a code dive, and perhaps it'll be a bit longer. And then I'll just try to give you a demo if all my servers are up and everything is working. So what do we try to do with it? And of course, as the name says, we're just trying to build programmable overlays or SDN overlays with the help of VPP. And of course, the recipe for an overlay varies per person. We have a specific recipe for our use cases. So we have like 4 basic pillars. One of them is we want to have a data-driven control plane. Why? Because for scalability, I guess, principally. So what this means, if you consider that within an overlay, you do all the time mapping between the overlay namespace and the underlay namespace, you don't want to push all this information, all these bindings or mappings, as we call them, to all the nodes within the overlay. Instead, we would like, based on the traffic matrix between all the overlay members, to pull that information. So that's what I mean by data-driven control plane. Then these mappings between the overlay and underlay, we want them to be as rich as possible in terms of what they can convey. Simple use case would be you want to just convey connectivity information, but perhaps we want to do something more like ACLs or traffic engineering and so on and so forth. Then within the overlay namespace, of course, the logical thing would be to support v4, to support v6, but we would like to support something else. For instance, MAC as well, so layer 2 overlays, or even NSH. But that sort of thing, it's to be seen as we evolve. And finally, of course, we would like to drive everything from a centralized point, from an SDN controller. So this is like the high-level statement of our purpose in life as a project. And let me just now very briefly go through something very, very schematic that shows what we want to achieve. And, well, some of the things we have already. So if you consider this topology, and since I don't have a cat annoyer, do we have a cat annoyer? So if we have this simple topology where we have like mock-up topology where we have 2 branch offices, let's say, or 2 separate networks, and I'll try to catch it. I'm really bad.
Break it.
Wow, it's Dave. Strike 3 very soon, I'm guessing, with Maciek.
Turn it on for you. Don't point it in your face.
If we have these 2 branch offices or 2 separate networks, and they're connected by an underlay, I think I went 1 slide too far, or more slides too far. Okay, here. And we want to connect them, these 2 networks want to connect them over this underlay, and we want to use VPP as the enabler of this overlay. And in addition to all these components, we have this thing called the mapping system, which is in the sky. So it will be somewhere in the network. And it will control how this overlay gets built. So let's see how we would want to build this. As a first step, imagine that we have packets traveling from this host. They want to talk with the other host. And we want to build the overlay between the two VPP nodes. So the first packet would hit the VPP router. Let's imagine this is the first packet that ever travels between the two networks. So what we want now is we want some information about this destination router, about this destination overlay network, where it is attached in the network. So we send this request to the mapping system. Mapping system resolves it for us. We get a reply, and in the reply, we may get various sorts of information. As I mentioned, in the most simple of cases, we may get just simple connectivity information. That is, hey, if you want to talk to B that happens to be behind this router B, then just encapsulate to this destination. And encapsulate can be something generic. It can be VXLAN, for instance, or it can be LISP GP or GP. But I was mentioning that we could do something more interesting, like for instance, say you want to go to C, but now instead of going to C directly, you want to build like a source path, like go first to D and only afterwards deliver the packet to the destination router. Oh, actually this works. How? It can't work. Sorry about that. And finally, the last thing that I have here. Maybe you want to do something specific for a source. So let's say source A wants to talk to destination F. In that case, provide a given specific destination router. But if, say, another source wants to talk to F, we would be providing another sort of destination router. So we can control how packets travel across this overlay. Now, once the XDR obtains this information, I'm confusing myself, I'm using LISP terminology. Once this node obtains this information, we'll cache it for the reuse whenever other packets will come within the flow. So it will all the other packets that will come will be encapsulated, will be sent to whatever we decide is the destination. And finally, this is confusing, not being able to use this. Or actually, well, in the simplest of cases, we just encapsulate towards the destination. But let's imagine now this thing is multi-homed, so we have the possibility to use two paths to it. So maybe we want to use that the existing multi-path support. And finally, the destination just gets the packets, decapsulates them, and now forwards them to their intended destination. Sorry about that. And we're done. So this is basically what we want to achieve in terms of how the overlay is built. But in addition to that, we would like to do the following. So if we have some routers that just happen to communicate with the mapping system in the sky and obtain information about where the other destination nodes are within the underlay, so what's their underlay attachment point, if something changes within the underlay and somehow now the mapping system that may be part of an SDN controller learns this information, so like this guy changes its attachment point and announces it to the mapping system, we want the mapping system to push this information back to all the guys who obtained it. So now they can update their state and go to the right destination, so we won't be losing information. Okay, so that's it. That's it in terms of what one wants to achieve at the very, very high level. So let's now see how this maps onto VPP and at the very, very high level again, and then we'll dive into the code. So from VPP's perspective, what this means in the data path architecture, if you consider that generally, and I guess you've seen this all week, the list of nodes that would be traversed if you want to communicate, if we receive a packet on DPDK input, how does it get finally to a destination? How does it egress the whole graph? Well, this is just a tiny bit of the graph, just to give context to what I'm going to show. So the LISP data path would attach itself, and the colors are, they work. So the LISP data path would attach itself at the IP lookup And why it does that, it does it for two reasons. First, if you remember from the previous slides, we said we want to do both maybe we want to do source and destination forwarding. So based on who's the source and the destination, we want to decide where we want to encapsulate. So in this case, IP lookup gives us a very good destination lookup mechanism, and we want to replicate that, want to do source matching as well. So we slightly fiddle with it. Instead of looking at a destination address, of course, we're looking at a source address. But we will be doing an mtry walk as we do it in the IP4 fib. And finally, these two things together would give us a source dest match and an adjacency that we will be using further on to decide how to encapsulate the packet. So if all things go right and we don't have to drop the packet, we will most probably get to what we call LISP-GP encap node, where we will encapsulate the packet according to whatever the adjacency tells us. But more on that a bit later. And another thing important in LISP-GP's data path is that, well, we need to receive as well packets encapsulated. So that was the send or egress path. The ingress path works like this. So LISP-GPE as a protocol, so by the way, this is the protocol we're using for right now for encapsulating. It just so happens to be LISP-GPE, which is very, very similar to GPE. And it can be VXLAN, can be anything else. But LISP-GPE just so happens to use UDP port 4341 for data path packets. So everything that comes on 4341, we register for it, and we just get it in LISP-GPE input, which is our decapsulator node. So again, this is just the architecture. We will dive in a bit in the code in some minutes. Now, the other part that is important, so this would be the data path. The other part that's important is the control path. So in terms of the control plane, we have, well, for all intents and purposes, we have two important nodes. One would be the control plane lookup node, which generally will receive traffic if somehow in the lookup stage we don't manage to find anything. So that means we don't have a tunnel configured for this destination. Probably we should be going to the control plane to ask something. And on the ingress part from the control plane, LISP-GP uses port 4342 for UDP port 4342 for Lisp control plane packets. So anything that comes there will finally go to Lisp control plane input, and we handle those messages there. And now I'm pressing the wrong buttons. OK, so what happens if a packet gets to the control plane? And this will be just very high level. It doesn't really, I don't want to go too much into too many details. So for instance, if the data plane decides, and we're here, I hope you can see my pointer. If the data plane decides, OK, I have no destination, I have no tunnel for this destination, I need to do something. Well, control plane, please do something for me. Find me a forwarding entry. The control plane has a given logic that will first try to decide, do I have it by chance in something that we call generic ID dictionary? Do I have this information about this destination stored locally by chance, and somehow the data plane didn't get it? If not, well, then just go to, and this is not a node, so I'm trying to differentiate between the two with colors. The control plane will just decide, OK, I need to push a map request to the mapping system, in the sky, asking for this destination that I didn't know. After, let's imagine now this works well. So we get to the mapping system, and the mapping system replies to us with this information. So we will get on the ingress part, and this is a node in VPP, Lisp CP input, we get the map reply, or maybe we even can get the map request, but we get the map reply in this case, and the logic will take care of first storing it within our cache. As I said, we have a cache within the router, and afterwards do some processing on this mapping that we obtained, figure out figure out how it matches with our own state that we have in the router, what sort of, we know who wanted to talk to this destination, and we do some mix and matching of our locators or our attachment points with the destination attachment points, and finally program the data plane. So the control plane has this information, says, okay, this guy can be reached at point B in the network, I'm point A in the network, thus probably I should be installing a tunnel here in the data plane that says, if a packet comes for this destination that was the original request, then just insert in the data plane an entry that says, please do encapsulate all packets to these destinations and put as a destination in the encapsulation B and use myself A as a source, and that's it, and forward the packet. And that's it. So then with this, I'm done with the high-level architecture, and I will start a code dive. Are there any questions before I move onward? Okay.
Well, as you get into the code, I think you'll see particularly those two UDP port registrations are pretty much one-liners.
Yep.
To go, collect the goods, and in fact, IP UDP for us to a particular desk port is, it's just a well worked out one-liner to go hook up to the graph, and easily done from a plugin, easily done, from the main, the main goods.
Okay, so then let's actually start there. Or I wanted to go to the, can everybody see the screen? To increase the font size?
Yeah.
Oh, wow. No? Are we doing better? It's my whole screen now. Okay, so I'll just start with what Dave said. I'll move to the data plane afterwards. So this is the control plane, and what you can see here, I will move just to be able to indicate something here. These are the two UDP port registrations for the control plane. So we're registering here 4342 and we can register mentioning if it's V4 or V6, and we're listening for both. But let me now just go back to. Okay, I lost connectivity to my own thing. I'm just opening it now. This is weird. What just happened? Technical problems. Okay, good, fine. We're at the end. So at the same time, I told you that we're registering the data plane, that is 4341, and this is a UDP registration as well. So this is for all the ingress traffic that we'll be receiving for LISP GPE. And this is the init function. So this is what we do. And I'll try here to I think I'll just reiterate what Dave showed you yesterday, or what Keith showed you yesterday. And tell me.
I'm just going to get where I can watch.
So this doesn't do too much. It's just a simple init. But the most important part happens when we enable the LISP GPE code. So until now, when the thing comes up, we don't do anything. So we're not attaching ourselves. And that will be happening here. So the only thing that you should take away from this, if you ever look at the code, we build an interface, but that's not really important. We attach ourselves here in this part of the code to IP lookup, and we attach the LISP GPE IP4 lookup node. Basically, this is the source lookup node if you want. We had the destination lookup node in IP4 fib, and now we're adding this new one. Apart from that, we're doing one more thing. We're adding a default route. We're adding 2 here because it's for v4 and for v6. And let me just go into that. And what's worth seeing here is we're saying that if Lisp GPE comes online, then the default routes, v4 and v6, will be pointing to the control, the control plane node. And you can see that here. So if you remember, well, here we're saying we're adding an entry within the fib whose next lookup next index is actually this thing here, which is the index that we got when we registered our node. Apart from that, we'll get more into this when we'll see why we're using the rewrite header software IF index. This thing will be the information. So we're using the rewrite header. Now we're kind of overloading it, and we're using it to store information about the source fib that should be checked if something hits in the destination fib, but more on it a bit later. And here we're just setting it to default values, and then we're just simply adding the default routes. So nothing spectacular. So everything at this point, if you remember the slides, and I'll just go for a second here. Everything that we've added ourselves here, and everything that will hit a default route, which is here, oh, ouch. Everything that hits a default route will come finally to the control plane. So coming back to the code. Next up, you see here that we're adding to IP4 lookup the LGP IP4 lookup node. So let's go there and see what we do there. And we're here. So let's just skip for now the dual loop. And again, this is the node that does the source lookup and in the source fib that we built just for Lisp. So all this tricks about speculative enqueuing, we get the buffer that we have, and then because we went first to the destination fib, and this you'll remember from yesterday, we get from the buffer in the IP.adjacency data in the TX, we get the destination adjacency index. So we know from the buffer already what destination adjacency was hit. We take the destination adjacency from there, and then next, I told you, but I didn't show you exactly how it was built, we have within the rewrite header a pointer to the source fib that we should be hitting. So in the destination adjacency, we just store a pointer to what we should be using in terms of source fib. And this is the source fib index that we got. Now, in case this thing happens to be twiddle 0, which is not a value that should occur very often, and in our case is just something that says, okay, the default was hit, we don't have anything for the source, then we go to done. That is, we just go to the next, and this is the default next action, which is just send it to the control plane. This means we had nothing, we found nothing. If, however, we found something in the source fib, that, the source fib exists. We go do a lookup, and this is just some locally tuned source fib lookup mechanism. Is very, very similar to the IP4 mtry walk that we're doing in IP4 fib, just that it's slightly changed not to call all the functions that we have there. Just it's a bit optimized for our purpose. And then after we do the source fib lookup, we find the source adjacency index, which practically is our adjacency index. So we hit something in a source test fib, then we just tag the packet with this source adjacency index, as you can see here. So we replace the previous one that was put by the IP4 fib, and then we take this, we look up the adjacency because we need from it the lookup next index, which is this, and that's it. We're done. So we have the node where we should be sending the packet. So we've hitting the source dest fib an entry. We have the next node where we should be sending the packet. Typically, this should be the Inkup node. And we've tagged the packet with the adjacency index here. So now the Inkup will be able to use this information to decide how to Inkup actually the packet. So let me then stop here with this method. Actually, we've got to the end of it. And let's just briefly then go to the control plane, and then we'll see what happens when the control plane receives a request to map a destination. So I'll walk you through now the init of the control plane. This is just spurious stuff. We're initializing our own cache. We're registering, as I said, the 4342 ports that we have for the control plane, and that's pretty much it. But if we go to the lookup node, so basically this is where if something misses in the data path, remember we had a default. If we hit the default, that means we don't have any tunnel information. Just go now to the control plane. The control plane receives the packet exactly here. This is the method that will deal with it. We didn't even bother dual looping because this control plane code. So what it will do, all the normal things, but it will get here the source and the destination of the packet, and we'll just send the request to the mapping system saying, hey, this is some info that I've got in a packet. I don't know what to do with it. Please do tell me where I should be encapsulating to. And that's it. So with that thing, we're done. But now, when something comes back, if you remember, that's called the LISP CP input node. So the mapping system managed to find something. We get and to provide us something, we get, and this is I guess the simplest way to look at it. We get a reply, and now this information there can be either a reply or it can be something else. Let's just focus on the reply for now to see what happens. So when we get a reply, what we will do is, well, and we can safely skip most of the code. We will parse it, and this just takes care of parsing all the information that we have in the reply. But ultimately, the thing that we will be doing, and I'm just going to go very fast here, we will store that information. If you remember the graph that I showed you before, we stored this information, the mapping that we got, in our local map cache, and this is what we're doing here. And after we do that, so we program our own forwarding to say, okay, now I know what to do with this destination. Please do encap this destination from now onward. So we're still in the control plane, and now we're going to the data plane. Now we're calling a function that will program our own data plane. So this just is some logic to deal with the packet. So we have ourselves a given mapping. The destination has a given mapping. We try to mix and match them to finally decide what's the source of the Inkup, what's the destination of the Inkup, and ultimately, and I'll just jump because it's not worth digging into it. We'll call the API of the data plane that says that programs the data plane, and let's just jump there. So right now I'm just jumping between the two. Oh, oops. Okay, that's not the one. Okay, we're there. So if it happens, this mapping that we obtained in the control plane to be a negative mapping, so it may happen that even the control plane says, well, I don't know anything about it. then we'll just insert a route here in our source dest fib that says, okay, just drop the packet or forward it natively. In this case, it will just drop the packet because we don't know what to do with it. So we cannot Lisp encapsulate it. If, however, this happens to be a proper mapping that has all the information, a positive mapping, sorry, that has all the information associated to it, then what we do is we build an adjacency here whose lookup next index is in cap. So we're preparing our own adjacency that we'll be inserting in the source dest fib that says, okay, if you get hit, please do send to this following node. And that following node is going to be LISP-GP, IP4 lookup next, LGP in cap. We insert that route as in our source dest fib. This is like you'll see this a lot in the IP4 fib code. This is just like an IP4 insert route, just that here we're inserting in our dual source dest fib a route, and then we create a tunnel. And well, this is just for expository purposes. It's not really worth going into how we build all the tunnels. So we just build a string of bytes that we will be putting on all the packets. So we pre-compute what we need to, how we encapsulate the packet. Of course, some fields aren't, we cannot pre-compute them, like IP checksum or UDP length. Those will be filled later, but this is just a bunch of bytes that we will be painting on the packet. And this is what happens here. We just pre-compute that thing, and we store it locally. So we add the tunnel. Now we have that thing as well. And then after we added the adjacency into our source dest fib, we just pull it out to do a bit of fixing. I think Dave explained this yesterday, that this is one possible way of doing it. You just write the adjacency, then you get it, and you change for it. And this is the thing that was confusing probably some minutes ago, which is for the adjacency that's being hit, the rewrite header software IF index, the name makes no sense. We're just reusing a field that existed there, is our tunnel index. So within the adjacency, we store the information, the index, how we should obtain the information about the tunnel that we just created to know exactly how to encap our packet. And with this, we're done. So we've programmed our forwarding, and now all the packets that will be coming afterwards on the data path will hit this source dest fib entry and will be sent to the incap node. So let's go to the incap node. Oh well. So let me just go down. As usual, this will be the node. Let me jump a bit and avoid the dual loop. Now, there's not that much that happens here. So, but the important part is we're getting the packet. If you remember, we're rewriting the IP adjacency index on the TX with the adjacency index that we've hit in the source dest fib. We're getting that. Then we're getting our adjacency. So this is very similar. This is very, very similar to the IP4 fib until now. But now, from the adjacency, we're getting the rewrite header software IF index. That is, this is our tunnel index that we will need to retrieve our tunnel and then paint it on the packet. We get our tunnel. We make sure everything is fine, and then we call this method that the only thing that it does very efficiently, thanks to Damian. It encaps IPv4 and UDP encaps our packet. And it just so happens that it's going to be 36 bytes of data. And after this, we're pretty much done with the processing. The packet will be just sent to IP lookup now, because we've painted a new source and destination header, and IP lookup will take care of forwarding the packet through through the rest of the graph. If you remember, we had this discussion yesterday with Dave when we were like, and actually with Pierre today as well, when we were deciding, should we paint straight up the everything and send it to rewrite, or should we loop back to IP lookup a packet, and then IP lookup will decide if this packet goes, how it goes to rewrite, more or less. And here we're looping back to lookup. Maybe it's not the most efficient approach. Now, we're left pretty much with only one thing, if we don't want to jump into details, by the way. If you want to take a look at this, all the other things that you see here are in CP. The control plane part are just serializers, deserializers for our messages, some data structures that we're using for the map cache and so on and so forth. So it's not worth really going into them. But the last thing would be the Inkup. And for the Inkup, it's actually very, very, very little to do. Pierre showed this. That's it. We pop IP UDP Lisp GP in one hop, and then we decide based on the information within the Lisp GP header what's the next place we need to forward this packet to. So most probably, since we have only support right now for v4, this will be IP4 input, just to check that the packet is valid. By the way, if you want to check that if you do some processing on the packet and you say fiddle with IP headers, and then you want to recirculate it through the graph, you would send it probably to IP input to make sure that the packet is in good shape and something is not terribly wrong with it, instead of IP lookup. And that's it on the decap side. So very, very simple. And with that, I think I've done a full walkthrough of how the packets would flow through all this graph. And now, if there are no questions, I will try to do a little demo of this. In the meantime, I am listening if there are questions.
So Florine, I wanted to just say that this is a really nice specific example of a general model where you program the graph to say, if I have a session, if I have knowledge of a particular flow coming through, I'll process it directly. Otherwise, I'll encapsulate it and punt it to a control plane agent that eventually, with some luck at the protocol layer, will send me back directions how to program the sort of the dumb robot data plane. It's a really cool paradigm you can use with a number of mapping systems, with a number of interception schemes of one sort or another. And this is a really good canonical example of control plane and data plane, or sort of control plane agent built right into the forwarder itself.
Thank you. Thank you. Well, I like always to present it like ARP Lisp because it helps people see it better, but then it has this complexity of the control plane that it's not just broadcast. So here's the thing. We have, and this is a topology that I just have set up, and Dave will most probably recognize the IP addresses because he's using them he was using them in his setup. We have here a VPP node, 6031, another one 6033, and two client hosts. And the goal here is just to see how packet flows from this host to the other host and what sort of actions it triggers on our VPP machines. So probably would be a good thing to show you exactly how we're configuring things. Let me just do that. And now, right now, it should be a clean machine. We have nothing. I'll just run a script here. And before anything else, let me just show you what's in it. So we're setting up, we're setting up the two interfaces that we have. One is facing the clients. The other one, well, I don't have the. One is facing the client. The other one is facing the core. And we're setting up the IP addresses, and then we bring up LISP. That's the one-liner. It's a bit confusing, the name of the command. Probably we should be changing it. And then we're configuring something locally. Do I need to zoom in a little bit more? Do people see? Okay, okay.
Add up a little, maybe.
Let me do that then. Okay, I'm at the limit. Then we're doing this trick here. We're saying, well, for this IP address that happens to be our client prefix, we want to associate this locator set, meaning we want to build a binding between this the identity overlay namespace and underlay attachment point. And the underlay attachment point is the locator set, which happens to be built now only from one interface, which is Gigabit Ethernet 250. And these are some things that we're using for traffic engineering. We won't touch upon them right now. And actually, we don't have full support for them right now. And if you see, 250 is actually our WAN interface. So our WAN interface is the attachment point for this prefix. And then one more thing, we're saying, hey, the mapping system just happens to be at this IP address. And the mapping system, the reason why we're not doing this all of us together is it's an ODL LISP map server that I just have pre-configured. And coming back. So after we run that, okay, let me just shrink this a bit to fit better, hopefully. Okay, I'll zoom in again. So we just have the typical adjacencies built, plus we have the default, like I promised, for v4 that says, okay, anything that comes in here should go to adjacency 13. Let's try a ping. So right now I'm on client 1, so I'm on the host on the left, I'm pinging on the host to the right. And before doing the ping, I have here prepared the Wireshark to see exactly what will happen. And if the demo gods are with us, this will probably work. Or not. It's a bit weird to have that. Of course. Right. So I forgot to configure the other host. Right. And this should be good as well. Good. So right now we're seeing ping here, but we're not seeing it there. What you saw was this. First, we send an encapsulated map request. This is just Lisp terminology. We send a request to the control plane, to the mapping system. Hey, where is 6044 in this overlay? The mapping system replied, well, you know, this 6044, you can find it, and within this thing, you will see that we're providing, hey, this is a prefix, and it just happens to have a locator at 6033. So the attachment point is the other router, 6033. And then the ping flows. It reaches finally our other router. Now the other router itself doesn't have information about the source of the packet, so we'll send just the map request itself, try to resolve the world. And once it obtains it, pings start flowing. So you can see here, actually this would be a good ping. You can see here that packets travel encapsulated between the two hosts, and the packets go from 6022 to 6044, but they traverse the core of this underlay encapsulated 6031 and 6033. And well, let's try something else. Let's do at the same time a trace, and let's do a ping. So what you will see, because this is an easy way to discover if packets traverse the graph correctly. Well, packet comes to DPDK input, gets to Ethernet input, IP4 input. Then we go to LISP Inkup. Here, generally, the fibs don't trace packets. I'll let Dave answer why. I guess it's for performance.
What do you?
IP4 fib will never appear like
You're gonna see something if it does an adjacency drop, but mostly, yeah, you know, when it's a hit, you'll see where it goes, and that's really
Exactly.
and the encap string that's painted. So,
exactly.
yeah, it doesn't do extensive.
So basically, after it passes IP4 input, it gets to LISP GPE, where we're not showing enough information. We're just showing it hit tunnel 1, and then LISP GPE Incap, if you remember, encapsulates everything, sends it to LookUp again, and now LookUp forwards it to rewrite transit, where we're sending, as you can see, originally we were sending here 6022 to 6044. Now in rewrite, we're 6031, the source, because we've encapsulated, and the destination is 6033. And then we just go to the output nodes, and out they go, the packets. And if we look at the return packet, well, it will be slightly different because we're listening on the UDP port. So it comes to IP4 local. If IP UDP lookup, this finally means, because 4341 is the LISP GPE input, we forward to LISP GPE input, which takes the packet, decapsulates it, and forwards it to IP4 input, as I told you, to do all the proper checksums, and then the packet goes on its way, the usual way through VPP. That is, it will get to lookup, to rewrite, and finally gets delivered to the local host from the point of view of this VPP router. That is 6022, because that's the destination on the return traffic. So with that, I've finished my part of the presentation. Any questions?
What did you find hard?
That was awesome, dude. Right.
Yeah, Keith.
Apparently
Keith.
Nothing would be my guess based on that. That was awesome.
Thank you,
and
Keith.
very nicely done. And we already know Dave thinks very highly of what you've done as well. Really nice job.
Yeah.
Thank you very
So,
much, guys.
I know he can obviously speak for himself, but the standard question, when you're going through this and learning by yourself, I might add, what was the most difficult thing to kind of get your head around, your most difficult thing you were stumbling over, and how did you get past it, and how was it after that?
I should have prepared the answer for this. Now I have to think.
Thinking is encouraged, but not required.
Look at me, I'm
Just
living
do it.
proof.
Yeah, you're right. So I think apart from the idiosyncrasies of the code, which of course everybody has noticed, I happen to like them a lot once I learned them, but I didn't really find them that difficult to adapt to. What I found difficult is to do a big deep dive from, say, IPFib, and finally understand how an interface comes up, what all the things that are built when the interface comes up, and finally how you get the rewrite to work. Just all the mechanisms from a very high level to very deep. And then, well, I guess it was hard to do the full loop of the thing. In other things in the code, well, Pierre was spot on with the stuff I had to stare at the NQ algorithm a lot to finally understand what happens there, but it's just a matter, I guess, of time ultimately.
You didn't, well, Yeah, you didn't have to mess with it. You just wanted that level of confidence that it did indeed work.
Yes,
Yeah.
it's just the way I work.
Yeah.
Yeah.
Understandable. Well, thanks very much, dude. Awesome job.
Yep.
Thank you.